Hello, I'm Li-Kuang from National Tsinghua University in Taiwan. In this presentation, I will talk about Outlier-Aware Training for improving group accuracy disparities. Classifiers that use standard training can achieve high average accuracy, but perform poorly on certain minority groups. The standard training refers to ERM, which minimizes the average loss during training. These models often spuriously correlate attributes such as the existence of negation words in a sentence to frequently co-occurring class labels. More specifically, we can partition a dataset into groups, where each group is a set of examples with a combination of a spurious attribute and a class label. For example, with fact verification using the fever dataset, the task is to classify whether a provided evidence supports, refutes, or does not provide enough information to a given claim. The spurious attribute in this dataset is whether the claim contains a negation word. ERM models would spuriously correlate the label refutes and negation words, meaning that when the model sees that a claim contains negation, it would be more likely to classify the claim as refutes. Based on this attribute, each class can be split into two groups, with negation and without negation. That means we will end up with six groups from 3 labels and 2 attributes in this dataset. Let's look at a concrete example. The claim Louis Fonzi does not go by his given name on stage, which is in the supports class, contains the negation word not. Since this example is labeled supports, it belongs in the group supports with negation, and is very likely to be misclassified as refutes. The standard model performs quite well on the overall accuracy, but fails on the supports class examples where the claim contains negation words. We call the supports with negation group the worst group, or the minority group. Our example, Louis Fonzi does not go by his given name on stage, is more likely to be misclassified as refutes because the claim contains the negation word not. So, we have the problem that ERM models don't perform well on these worst groups. Our goal is to improve the model performance on the worst group. Methods that use group and attribute information during training can effectively improve worst group accuracy, but are expensive to annotate. We focus on improving one of the methods that do not require group information during training, called Just Train Twice, or JTT. In JTT, the ERM model is first trained on the training set. Then we classify the training set with the trained ERM model. In doing this, we obtain training set examples that are correctly classified and examples that are incorrectly classified. We call the incorrectly classified training set examples the error set. In the next step, we upweight the error set from the training set, and an ERM model is trained a second time with the training set containing the upweighted error set. The weight for upsampling the error set is a hyperparameter that is tuned on the validation set. In our proposed method, we focus on the step where the upweighting happens. More specifically, we think that the error set may contain untrainable or out-of-distribution examples, which we will call outliers for simplicity. When the error set is upweighted, the outliers get upweighted as well. The outliers that get upweighted then might make the performance of JTT less effective. Thus, we propose to remove the outliers from the error set before upweighting them. This way, we can train on a cleaner upweighted error set, hopefully improving JTT's performance. The threshold for removing outliers is another hyperparameter that we tune on the validation set. To remove outliers, we use the Mahalanobis distance method. We extract the second to last embedding layer of the model and calculate the Mahalanobis distance between the embedding and their class mean for each example in the error set. If the embedding's Mahalanobis distance is greater than a threshold, we say that it is an outlier, and we exclude it from the set of examples to be upweighted. To visualize this process, you may imagine each dot in the t-SNE figure is an embedding. In the top left corner, you can see the green and brown dots, which are deemed as outliers because they are too far away from the... In the top left corner, you can see the green and brown dots, which are deemed as outliers because they are too far away from the mean. Since we improve upon JTT using the Mahalanobis distance, we call our method JTT-M, where the M stands for Mahalanobis. After we remove the outliers from the error set, we can upweight and train the model like JTT. Now let's look at our experiments. We used two text datasets to evaluate our method. The first dataset is fever, which is a dataset for fact verification. Each fever entry contains a claim and evidence. The task is to predict whether the evidence supports, refutes, or does not provide enough information for the claim. The second dataset is multi-NLI, where the task is to predict whether the relationship between the given hypothesis sentence and the premise is entailment, contradiction, or neutral. For both of these datasets, the spurious attribute is the existence of negation words in one of the sentences, which is the claim and the hypothesis respectively. The attribute spuriously correlates to the labels refutes in fever and contradiction in multi-NLI. So let's have a look at the results. There are two indicators we want to track, the worst group accuracy and the average accuracy. We ran each experiment 5 times and took the mean and standard deviation. Paired t-test is run on JTT and JTT-M, and critical value for significance is 0.05. ERM, as we have seen previously, performs really well on average, but quite poorly on the worst group, which is the support class with negation. For JTT, we can see that it has improved performance on the worst group, but at the same time the average accuracy drops slightly, which is what usually happens with methods that aim to improve worst group performance. With our method, we are able to achieve significant improvement on the average accuracy, but no significant changes on the worst group on the fever dataset. On the multi-NLI dataset, we can observe similar patterns, with the worst group performing much worse than the average accuracy with ERM. JTT is able to improve the worst group accuracy at a trade-off on the average accuracy. Our method manages to maintain the average accuracy while making significant improvements on the worst group accuracy compared to JTT. Now let's take a closer look at the performance on each group. On the fever dataset, our method made a significant improvement on the refuted class. Our method made a significant improvement on the refutes class with negation, which is actually not a worst group. Since there is not much decrease in performance on other groups, this means that the improvement on this group is what caused the significantly higher average accuracy between our method and JTT. For the multi-NLI dataset, our method has a significant improvement on the worst group with neutral class with negation, which maintains the same average while maintaining the same average accuracy as JTT. So now that we know removing outliers can improve worst group accuracy, or at least maintain it while improving the average accuracy, we want to know what exactly caused the improvement. First, we check the percentage of detected outliers in each group in the error set, which can be seen as the percentage of examples that we removed before upweighting. We found that the class supports in fever and the class entailment in multi-NLI has the highest percentage of outliers. In fever, the percentage is much higher than in multi-NLI. However, in fever, However, in fever, the percentage is much higher than in multi-NLI, at almost over 30% for each. At over 30% for each group, while multi-NLI only has around 8 and 5%. While multi-NLI only has around 8 and 5% of examples removed. Second, we sampled 100 examples from the set of outliers and the set that aren't outliers, and tried to see what's different about them. We found a much higher percentage of annotation errors in a set of sampled outliers, with 24 and 10 for each dataset, while the non-outliers only contain 1 and 4 annotation errors. From the two observations, we concluded that 1. The Mahalanobis distance method can detect at least a subset of annotation errors as outliers, and 2. The improvements on either the group or the overall performance may be partially due to the removal of these annotation errors. In summary, we saw that the ERM model tends to perform poorly on certain worst groups. Even though JTT can improve worst group accuracy by upweighting the error set and training on it again, it can benefit from our method, which removes outliers from the error set before upweighting it. In addition to improving JTT, we also found that our method can detect. In addition to improving JTT, we also found that our method can detect some annotation errors from the error set, and their removal may be why our method is able to outperform JTT. Exploring the effect of using other outlier detection methods and more efficient ways to tune the extra hyperparameters from our method are important directions of our future work. Thanks for listening to my talk, and if you're interested in our experiments, you can find our code on GitHub.